Okay, good morning everybody. Let's talk a little bit about deliverable 5. Any questions? All good? Everyone clear on what they're doing? Everybody have a pair of digits assigned to them? Everybody's KNN algorithm recognizing their 2 digits? A couple of nods, yes? Okay, good. Okay, so let's push on through and finish up today with our theme on interactive system design. Your guest lecturer last time, Joshua Powers, walked you through the design process, part 1 and 2. And lecture 8 ended with a discussion about user testing. We're looking to measure something from our users. In some cases, we're looking to see the mean response time. Sometimes we're interested in standard deviation. Are our users experiencing very different experiences when they interact with our system? We'll come back to user testing in week 10 when you're going to switch over and start working on your ASL educational game. So far, so good? Okay, so let's finish up the last lecture on design today, which is talking about designing information spaces, and we're going to be focusing in this lecture particularly on creating new kinds of information spaces. For most of you, dealing with the Leap Motion device and the data sets that it generates is a new information space. You're going to create an educational game around this novel piece of hardware and hopefully create an interface for your user which allows them to navigate quickly and easily through, which will be for them a new informational space. Okay, we will then switch gears and perhaps starting today, but mostly next week, we'll be talking about cognitive psychology. Obviously, we could spend a lot of time talking about that. We're going to touch on just various aspects of cognitive psychology that are relevant for HCI design. We'll start, as we usually do, with some of the more objective or the more easy aspects of cognitive psychology to understand, like mental models. How does a user go about building up a mental model of your ASL educational game? And we will gradually march through a couple of other aspects of cognitive psychology that become increasingly subjective until we get to affect, which is the fancy psychology name for emotion. Okay, so that's where we're headed. Let's come back to informational spaces to begin with. Let's start with some of the most obvious ones. So usually a user interface is a window onto an information space. Some of the most obvious ones we're familiar with, in the early computers, in the early days of computers, we had text-based, command-based interfaces where the exchange medium was the computer itself. We had a keyboard or a mouse. We type into a command prompt and it would write some text back in response. Starting in the 1970s and then into the 1980s with the advent of personal computers, there started to be a broadening set of people that were interacting with computers. Not all of them were technically savvy, so the text-based interactive format didn't really make sense. So there was a big push in the 1980s to create more intuitive views onto the underlying information space of the computer, and thus was born the WIMP interfaces, which was some collection of windows, icons, menus and pointers and so on. They're so ubiquitous today, they've sort of blended into the background, but that was a huge advance, as you can imagine, over a blinking cursor and a command prompt. The exchange medium here was also the computer. What do we mean by the exchange medium? You can think of this as the two-dimensional plane, right, which is often the computer monitor. The user is seeing this two-dimensional window, which is a projection of something behind it, right? And so in today's lecture, we're talking about information spaces, the thing that lies behind the glass. Most of the information space is hidden from the user. Hopefully, your user is going to know nothing about 4-dimensional NumPy arrays when they attempt to learn ASL through your system. But you are going to have to decide in weeks 11 through 14 what aspect of your system are you going to project to the user. right? So what are we going to project on that two-dimensional plane? How do you intelligently select what to show, and most importantly, what not to show, to communicate what the system is for and help the user learn ASL? We're not going to spend too much time today talking about text-based and graphics-based user interfaces. We're going to spend a little bit more time talking about what are now known as tangible interfaces, where the exchange medium is not just the two-dimensional plane anymore, but the interface projects into the physical world. The user is manipulating something that exists in the real world, and that is their way of communicating with the information space behind it, right? An obvious example of that is your smartphone itself. Of course, there is the two-dimensional plane, and there is a lot of going on the surface, but how you hold the device, how you orient it in space, and how you move that device around in space is also a way of interacting with the apps and the internet that lies behind the smartphone. Okay, so one way of thinking about what's sort of state-of-the-art in HCI today is breaking the plane, so projecting technology out into the world with us and allowing people to physically interact with objects and devices and Wi-Fi spaces and so on. That's the space that we're most interested in today. Okay, let's have a look at an example of this tangible interface. Or a type of tangible interface, where it's very clear that we're not just dealing with a two-dimensional plane. In the demo you're going to see in a moment, you'll notice that the users are interacting with physical objects. Those physical objects, in turn, are going to interact with the two-dimensional plane, and that interaction is going to project downward into an information space, and something is going to be projected back to the user. Remember, in the very first week of class, we had this feedback loop where the user does something and sees the result of it. In the React table demo, most of what the user is doing, the input of the user to the system, is going to be through physical objects, not directly by touching or tapping on a two-dimensional plane. What you'll also notice in this demo is a whole new set of visual metaphors. But the React table, as you'll see in a moment, is a way of creating music. So we're going to see a mixture of not just visual metaphors, but also auditory metaphors. Finally, in the React table demo, they are going to try and connect vision and sound to create metaphors. So there's going to be a mixture or a connection between what the user or what you see and hear. Okay. Okay, I'll just pause things here for a moment. We'll watch the rest of this video in a moment. I don't know if this quite qualifies as music. It's definitely not my choice of music, but there you go. What are some of the metaphors that are already at play in the React table?
I mean, I see the Euler identity all over the place.
What's that?
I see the Euler identity all over the place.
The Euler identity.
Yeah.
What is the Euler identity and how do you see it in the React table?
So we have a Tesla coil visualization.
Okay.
And so that would be an indication of the electron. Lock sphere is built around the Euler identity, so it's the Saturnian.
Okay.
We have different nodes, and it looks like they're being used in an Euler tour because they're all parallelized, at least visualized if we look at the big.
Okay.
Do you know have like a real like lag time between the visualization and the sound?
Okay.
So it seems like it's in the ECS framework. So again, another like Euler-based framework. So it all seems to be based around the electron.
Okay.
Design of the electron.
Okay, so remember our discussion about affordances? Different objects project different affordances to different people. That is one possible interpretation of what's going on here. Yep.
I see a knob metaphor.
A knob metaphor, right? Why the knob metaphor?
Just like, because he twists it, so it looks like he's turning a knob.
Exactly. So there's a lot of hints here about the knob metaphor, to be non-technical for a moment. But why the choice of that metaphor in this application?
Yeah, there's a direct like action and reaction.
There's a direct action and reaction. All right, the moment you turn the quote-unquote knob, there's a reaction. So these are all descriptions of what the metaphor is and how it's projected. But I'm getting at the why. Why did they choose that metaphor over another metaphor?
Does it have something to do with how soundboards are operated?
It has something to do with how soundboards are operated. Remember our discussion a few weeks back about conceptual consistency, right? Within the first few seconds of seeing the video, hopefully you realize this is some sort of audio mixing or music creation software. The moment you realize that that's the application, there is a whole set of expectations that most people bring to bear on this system, right? Long before the React table in computer music, there were mixing boards going back, and most of them had on their surface knobs that you would turn, right? So the React table developers are explicitly trying to bring those expectations to bear here by picking those particular metaphors.
So the reactables, are those like flight simulators and that robot that we saw that if you put your hands in they weren't going to come over, or is it much more literal like the Minority Report computer?
So there's the Minority Report idea here, absolutely, right? The interactive surface, the flight simulator.
Yeah, you know,
demo.
when they're in the cockpit and actually flying, doing the knobs and you see the screen. Is that still a reactable, or does it have to be much more?
So the React table is the name for this specific application, right? So you mentioned the flight simulator where you actually reach in and there are either virtual knobs or a steering wheel and so on. Absolutely, right? So there's sort of a virtual reality dimension to this as well. They're mixing physical objects with virtual objects. So in that way it's common, but they're mixing it again together in this application for a particular purpose, which is to suggest affordances, ways in which you can interact with the React table.
I see, so the center dot makes me think that this kind of mimics an orchestra.
Okay, so the center dot, right? What is the center dot? You mentioned an orchestra, which is the right idea. It's the conductor, right? So there is some sort of central organizing thing or point or nexus in this system, which is the dot in the center of the table. That's where the conductor metaphor ends, though. Usually the conductor is sort of deciding what happens. That's not quite the case. What is the dot doing?
The initial node maintains a connection as long as it's tethered.
The initial node maintains a connection. What do you mean by node? The center dot?
The first node would be the bottom left.
Okay.
Yeah, so it has a tethered connection. And anything that's within a certain radius of that node will again be added to the network.
Exactly. So let's stick with that for a moment. The radius, right? There's a lot of circles in React table. Why the radius? What is the metaphor that is being advertised by the radius or the circle?
I think maybe the metaphor is provide some energy to the small robot.
It provides some energy. That's the line. Provide some energy. What is the circle doing? So the line here is obviously communicating something from this physical object to the virtual object, the dot in the center.
The way it kind of seems like the center dot's like the output, where like if it doesn't reach that, it's not getting translated into sound.
Exactly. So if something does not reach, quote unquote, the center, it is not passed on to the speakers. So what are the circles about? What does this dashed circle represent?
Tethering distance.
close.
So that top node is pinging the other nodes, so it's just the radius that it can ping.
It's the radius that it can ping them, right? So these two objects may or may not be within hearing distance of this object, right? This object, or the virtual dot, is within hearing distance of this object, right? So they're using like the radar or the listening radius. That's the metaphor with circles, right? So things that are too far apart, they can't hear one another. And the lines are doing what? At this point, we've got two lines. Forget the radar line for a moment. What are these two lines advertising? What's the affordance associated with these?
Showing the wavelength and intensity.
The wavelength and intensity. So the shape of the line is telling you something about the quality of the sound that's being passed from the dot to the object or the object to the dot. Object to the dot, dot to the object.
Object to the dot.
Object to the dot, right? So sound is flowing from this object to this object and from this object down to this object. How can you tell that exactly? What are all the hints here, both visual and auditory, that are trying to communicate that information to you?
It's kind of just like the middle is your ear, and you can see the closer ones have like higher amplitude.
Okay.
And you can see that when it, like that thing like plucks them or whatever.
Right.
You can see that they're making louder sound when they're closer.
Okay, so there's a lot of things going, the plucking of the line, right? Another auditory metaphor. What else tells you that stuff is flowing down towards the center, not a conductor that's sending information out?
There was a pulse like in the outermost node to a more central node, and so there's a direction that we're just
Yeah, so in some of these, there's a visual metaphor showing things literally flowing from one to the other, right? The idea is everything is flowing down to the center where it is being combined, right? Again, some other auditory metaphors, right? This is, one way of thinking about this is a sound mixing table, right? We're literally mixing together different kinds of sounds. Okay, let's watch the rest of the video, see what other visual and auditory metaphors you can pick up on. Okay. Other metaphors. How intuitive do you think this system is to use? Maybe yes, maybe no. I've never tried it. Who knows? Okay. An interesting HCI demo, though, again, of where the interaction is not going on directly with the surface, but people are interacting with physical objects in 3 dimensions, right? 3 dimensions is nice because it allows rotations. We can place objects in different 2-dimensional locations on the surface. You can rotate the cube and place one of the 6 faces down on the table. 3-dimensional rotations, if that's what the user is doing, is notoriously difficult with a mouse or even with a touch screen. If 3-dimensional rotation is important to your application, or with the hand, 3-dimensional rotation, it's nice to allow the user to remain in 3 dimensions rather than forcing them to work in a 2-dimensional plane by moving a mouse or moving their fingertip on top of a 2-dimensional surface, right? As always, it depends on what we are facilitating, how we are helping the user to do what they do. Okay, tangible interfaces are not the only interfaces that allow visual and auditory metaphors. Obviously, GUIs back in the day were meant to represent, were designed to allow you to translate your very messy desk into a very messy desktop. What are some of the metaphors in a GUI? Desktop is one, obviously. The trash bin, yes, which this user should make more use of. What else?
Folders.
What's that?
Folders.
Folders, files, folders, right? Drag and drop, that very term, right, is very evocative of the kinds of affordances that most GUIs afford. Okay. There was an attempt back in the day to try and escape the two-dimensional plane by making lots of interesting eye candy and sort of escape the 2D plane. How many of you use a more than two-dimensional desktop? I don't. It didn't really seem to work. We will look very briefly at the Bumptop demo here. Still the two-dimensional plane, so not a tangible user interface, but sort of virtual tangible interface. Okay. Why aren't we all using Bumptop desktops?
So that seems like it takes all of the improvements that you get with a digital interface where you can like see a large number of things all at once without having to like sort through them, and
Right.
just does away with all of them.
Right, so we're pushing into the three-dimensional plane, which is nice if you need to do things in 3D, but 3D comes at a cost, which is occlusion or distortion, right? So you're looking at one of your JPEGs, which is pinned to one of the virtual walls inside the Bumptop box, and it's distorted because it's not facing you head on, right? One of the underlying rules in HCI and lots of other domains is keep it simple, right? Unless you really need 3D, if you focus more on what you can do with, for example, connecting a physics engine to a desktop interface and lose sight of what someone wants to do with a desktop, you can get into trouble. Okay. Question?
I don't feel like this one because in my mind this is a very computational intensive, so the device is not enough for such a scene.
Absolutely, right? So you can imagine that Bumptop is very computationally expensive to begin with.
And when you are talking about the interfere with other stuff, non-relative stuff,
Right.
I think maybe in our home we can just clean the desk and remain just one item on the desk, and that's make us focus on the item.
Exactly, right? So you clean up your desk so that only the things that are relevant are in view and everything else is hidden away.
Yeah.
In the case of the Bumptop, the idea was to make that task as easy as possible if your desktop looked like the one on the top right, right? I want to collect all of this stuff and not throw it in the trash. I need it for later, so I'm going to collect it and then stack it and then set it aside, right? That was the idea behind the Bumptop, which for some people may be useful. Rather than dragging and dropping a whole bunch of files into a folder manually, could you build on people's expectations about the physical world and simplify that task?
Couldn't you say that somebody who's going to individually drag and drop whatever 20 files on their desktop is already like not really using everything that that interface offers them?
Possibly.
Because you can already like select multiple things and move them all at once.
Of course, right. So most modern desktops make that simpler anyways, right? Do you need all of the bling of a physics engine and this illusion of 3 dimensions? Who knows? It's probably overkill. Yep.
That's a bit of an assumption, though. I work with someone who just edits video.
Okay.
He drags and drops files.
Okay. So
Not exactly the most efficient manner.
exactly, right? So again, this is a subjective enterprise. Some people may find that this is useful depending on what they spend most of their time doing with their computer. It depends on the person and the activity. Right? Okay. Okay. So let's move on. So again, we're moving towards talking about information spaces, the structure behind the interface. And of course, we can go about creating very different kinds of views onto an information space. And as always, we want, as HCI designers, we want to think carefully about how to design that interface for whom, right? What subset of the information space do they want to see? Different choices about the interface, implicitly or explicitly, rely on different ways of thinking, right? So obviously, if we're dealing with Windows and Windows in Windows, GUIs, they're relying on the human visual system, which is very good about spatial organization or seeing spatial patterns, right? So Bumptop tries to hide a lot of things, which is sometimes useful, but other times we want to spread things out, have multiple windows open in parallel, and very rapidly copy and paste from one to the other, or organize our windows. Often we're very good at organizing information in a two-dimensional plane. We want to be able to see everything, sometimes. Other times, we want to try and rely on the human ability to organize information hierarchically. So in that case, we may want to rely on menus and drop-down menus. Why is hierarchical organization useful from an activity point of view? Why not take all 321 functions in an app and have them in one long flat list?
It's easy to search.
It's easy to search. I'm going to take all 321 functions and organize them alphabetically. I'm going to make it very easy for you to search. Why do we want hierarchy?
Someone may not know exactly what a particular function is called, but they know how it's categorized.
They know how it's categorized, right? I just bought a new smartphone and my alarm did not go off this morning, but luckily I woke up and I'm here. When I go back to my office, I will have to go find where the turn on the alarm buzzer is. It's a new phone. I haven't worked my way through this hierarchical menu system before, but I have a pretty good idea of where it is. I don't have to read through the entire flat list. We all have an increasingly common understanding of where certain functions are in a menu hierarchy, regardless of the operating system, regardless of the phone, regardless of the app, right? Where is something? In an increasingly complex application or piece of technology, there's something I want to do, and I want to navigate quickly. I want to go find that piece of information quickly. I could perhaps perform a global search, but failing that, in a hierarchy, I've got a pretty good idea about where generally it's going to be located. Okay, I know at the other end of the scale, I know this application or I know this technology extremely well. I don't want to see anything at all except a blinking cursor, right? I want to be able to type in, because I've memorized and I know all of the functions, I want to be able to type it in as quickly as possible. So if we're dealing with advanced users or users that want to get things done with a minimum amount of time rather than clicking their way through a menu hierarchy, command line based interfaces make sense. Once you get really good at doing things at the command line, you're typing the same sort of commands over and over again. You realize you always type command I and then J and then K. So you create a new command M, which pipes the output of command I into the input of command J, which in turn is piped into command K. You start to pipe or put pieces together and increasingly speed up whatever your activity is. Pop-ups, kind of controversial. We want to be alerted about certain events that happen in the real world or happen online. So they're they're mostly invisible, but we want to be told about them when they happen. What's the particular challenge about pop-ups?
How much is enough?
How much is enough, right? Whatever it is these days, it just seems to be too much. Very difficult to write a piece of software that embodies a pop-up because everyone has very different thresholds about how often I should be reminded, when I should be reminded, when I should not be reminded. Lots of context behind pop-ups. Tricky to get that one right. Okay. very different kinds of interfaces, and depending, we want to choose these depending on what our users are trying to do. If I want to get everything out of the way and just let me do my thing in as short a time as possible, if that's what you're hearing from your users, that should suggest very strongly which of these you choose, rather than trying to create Bumptop and make this very fancy visual thing because it's cool and you want to create it, right? Okay. All right. So all of these are different ways of organizing information or views onto an information space. So let's talk about information spaces themselves. They are not that non-intuitive. They're pretty straightforward. An information space is some sort of space filled with objects and data. People are usually observing that space from the outside, but they may also be able to enter, literally or metaphorically, that information space and then navigate inside that information space to carry out various tasks. Of course, an information space doesn't have to be virtual. There's a lot of interesting physical information spaces you can think of. Transportation hubs like airports and train stations are great examples. You have people moving in a common space and they have particular activities in mind. They're trying to get from point A to point B in as short a time as possible. Others are trying to do it with changing tube stations as infrequently as possible. What are people trying to carry out inside this space? So if you think about an airport and a train station, forget about all the virtual displays. In the old days, there were paper schedules, timetables, and so on, right? Okay, so in an information space, either virtual or physical, we have a conceptual information structure. This is sort of like the foundation for the structure. And then we have for the space, then we have the interface onto it itself, right? So in the case of supporting an activity like travel, the conceptual structures, the things that make up this information space, are things like routes and stations, times, railway car classes, and etc. Once you have all those conceptual objects, which are obviously going to be relevant for someone who's trying to get from point A to point B, how do you organize that information? We can obviously create timetables. Where do you put paper timetables in a train station? Train station is big, lots of places you can put a timetable. Where in that space does it make sense to put that particular type of signage?
Next to the ticket counter?
Next to the ticket counter, right? I want to pay, and I'm going to pay depending on the different kinds of routes, right? So already we're starting to think about the relationship between the conceptual structure, what someone is trying to do in that space, and what interfaces we should create and where we should place them. Okay. Information spaces, at least when we're talking about virtual information spaces, are themselves hierarchical. We'll take the obvious example, which is the internet itself, the information space. Usually, if we do this right, each higher level in the information space has an interface which provides an abstract projection of the thing that lies below it. So if we pick a particular layer in the hierarchy that is the internet, which is an individual web page, we can think about that single web page as an information space. Someone is moving about through that web page. Conceptual objects are things like text and images, metadata, and document structure of the page itself. The observer does not see those objects directly. They're seeing interface analogs of those structures, right? The format of the page itself, print format, mobile app format, and so on. So even within an individual web page, there are different interfaces onto the things that make up an individual web page. Web pages are then put together into the internet. So now if we think of the internet as a whole, and these were some early snapshots of the structure of the internet itself, which now is so large it's impossible to create a good overview of what it actually looks like. If you think about the internet as a whole, the conceptual objects are now different, right? The things that connect together the parts of the internet, which are web pages, are things like links between pages and search and so on. Not easy to get a good interface onto the internet directly other than these days global search. So you can pick different kinds of information spaces like web pages, the internet, apps, computer games, and Leap Motion, the Leap Motion SDK itself, and ask yourself, what are the conceptual objects that make up that information space? And then what are the interfaces that are provided onto those objects? Let's take the case of the Leap Motion SDK, which you're all now very familiar with. What are the conceptual objects that make up the SDK?
Hand, finger, like all of these different
Okay.
objects we basically send to the computer.
Right, so hand, finger, bone, coordinates of bones, those ones are pretty obvious. There are some other ones that are less obvious, that are part of the conceptual structure of the SDK, but are not necessarily so obvious through the interface, which is the code itself, right? The bone constructor and the finger constructor and so on.
Sort of like documentation fall into that?
The documentation is a description of the underlying information space, which is a good point, right? So somewhere in that documentation, there is description about the underlying information space, and in the documentation, description of the interface itself. You can call the bone data structure and get back this kind of data.
Do you consider the, I guess, I don't know what it's called, the box that is the bounding box for your accurate gestures?
That's a great example, right? So the visual cone, if you like, that exists in which the Leap Motion can see the hand. That is an important part of the conceptual structure of the Leap Motion system. The interface doesn't directly give you access to that, right? I don't think you can query the coordinates of that cone or that prism, but it is an important part of the system, exactly. So the interface kind of hides that from you, the developer who's using the Leap SDK.
Let's have the controller, the frame, the Leap Motion surface.
Okay, so there's controller and frame and service and so on. Those do have a correspondence in the user interface itself. There's also the cameras and the infrared data, right? Which in some of the demos you actually see, like in the visualizer. They're there, they're not immediately accessible to you in the interface, right? For good reasons, that information is kind of abstracted away. But at least if you're developing stuff for Leap Motion, you should be aware that that is a part of these information spaces. Okay. Everyone got a general good handle on the difference between the conceptual structure underlying the system and the interface, which is a view onto it? Okay. Okay. So let's think about creating new information spaces. This is one of the most interesting things about HCI design. Sometimes we're creating web pages and we're using familiar interfaces, but sometimes you're identifying a particular group of people in a particular activity, and there is no good technology to support those people conducting those activities. So we want to create a brand new type of information space. You can think about the early days of virtual reality or the Leap Motion device. We're going to talk about cybernetic devices towards the end of the class. These emerging technologies, people are somewhat unfamiliar with them. They get the general intuition of a cybernetic device, but how do I interact with this new piece of technology? It's not always immediately obvious, so we want to try and structure that space and provide a view onto that new space that is familiar, recognizable, learnable, memorable to the observer. How do we go about translating the messy world of human needs into the clean world of information spaces? Josh P. last time walked you through some of this design process. What we're going to focus on now is sort of the philosophical side of this transformation. How do we conceptualize a domain of knowledge? In the early days of GUIs, mostly at Microsoft, but also at some other companies, they were looking at what people were going to do with personal computers. And the most obvious target demographic at that time was office workers, right? That personal computers were going to be used in the office. So if you walk into an office, what do you tend to see? You see a whole bunch of desks with desktops. And on those desktops are huge stacks of files and folders, right? They took the messy world of physical offices and boiled that down into information spaces, which became operating systems, and GUIs, which were views onto that operating system that borrowed all of those ideas from the physical world. Okay. In the act of choosing that conceptualization, someone somewhere, or a group somewhere, must have said, let's try, with all this stuff, let's try and create these things called files and these things called folders, right? The moment that activity was carrying out, that was what's known as choosing an ontology. We're taking this kind of amorphous space and we're imposing, we're distilling it down into things. That's an ontology. During that process, we're making decisions about what are the number and types of conceptual objects that will exist. If you look at all the GUIs that exist today, they differ from one another, but they all share the same ontology. Most of them have two main objects, files and folders, right? You could include the desktop itself as the third object. Let's pause for a moment before we get into coarse graining and fine graining and talk about choosing ontologies. What are some other technologies, and what are the ontologies that are associated with them? If we're talking about operating systems, the ontology is made up of files and folders and desktops. What are some other technologies and their associated ontologies? How many of you are learning Git for the first time this semester? A few of you, right? Git is a relatively new technology. It has a very sophisticated ontology. What are the basic building blocks in the Git information space?
Trees and branches.
Trees and branches, right? Okay, trees and branches, what else? What are some other important parts of the Git ontology?
Push and pull.
Push and pull, excellent, right? So trees and branches, nouns, push and pull, verbs, right? What else? What are you pushing and pulling? Clone and fork. I'm still wrapping my mind around the difference between cloning and forking and branching and so on. Sorry? Add and commit, right? Those ones are, add maybe makes sense, but committing is a little strange, right? Repositories themselves. Merge, right? So there's a pretty rich ontology underlying Git. Why? Why that choice of those particular objects for Git? You could imagine creating a distributed version control system, which is what Git is, using a completely different set of objects. Why did the Git developers decide on that particular ontology?
You can relate it to human actions. If you're pulling something down or pushing it into something.
Absolutely, right? So pull and push are kind of intuitive given what you're doing. It's a distributed version control system. So there is code or there is stuff out there. I'm going to pull, do something, and then push it back. Then somebody else might pull, do something, and push it back. Right? Makes sense. So that explains sort of pull and push. Why trees and branches and forks? Why that choice of ontology? Other ideas?
It just kind of like makes sense, like you're growing this tree and you're like constantly you're like building like on a certain branch and you're like growing it out further. It just kind of like makes sense.
It makes sense, right? If you think about a bunch of people that are working on a common code base, it's hard to think of anything else other than trees and branches and the branch itself growing, hopping from one branch to another, breaking a branch off and making it the seed of a new tree, which then continues to grow. There's something about that metaphorical space that just seems to make sense for collective code development. In the same way that if you're creating music, the conductor, the orchestra, turning knobs, turning volume up and down, modulating sounds, there's something about that action space or that ontology that makes sense for the activity of creating music, right? It seems kind of obvious in retrospect that trees and branches and forks make sense for this activity, But given a new set of people and a new activity, it's not always obvious in the moment what the appropriate ontology is for that activity. That is a big part of the black magic of HCI design. Yeah? Okay, we're going to talk about coarse graining and fine graining now, and to motivate this this concept, I'm going to show you another example from another information space, which is Overleaf. How many people have seen Overleaf before? Just a couple of you. How many have written text documents in LaTeX before? A fair bit of you. Okay, so let's start with LaTeX. As you can see in the image here, LaTeX is a particular way of writing text. It is not a WYSIWYG, which is what you see is what you get, like Microsoft Word or Google Doc. In Word or Doc, when you type, you see what you type, right? What you see is what you get. It's a common text editor, which makes sense for most people. However, if you're a technical person and you're writing technical documents, like, for example, deliverables for CS228, that document is a mixture of figures, enumerated lists. I don't know if there's any math in this deliverable. There is not. It's a nice way to introduce mathematics, pseudocode. You're mixing together a lot of different kinds of things. So LaTeX is not a WYSIWYG. It is somewhere between a code IDE, a programming language IDE, where you're writing code and compiling it into something else. In LaTeX, which in itself borrows that metaphor, you're writing a combination of text and markup items, which are then interpreted by the LaTeX compiler, taking that and turning it into, on the right, a PDF. So far, so good? Okay. So in the LaTeX space, there is a different kind of ontology, which is the raw text itself, various commands, begin and ends, which bracket things together. You can hierarchically include begin and end, so there's an interesting ontology underlying LaTeX. You can open up your favorite text editor and write LaTeX code yourself and then compile it. Or these days, increasingly, people tend to use Overleaf, which is sort of an IDE for LaTeX. In Overleaf, you can create a text document like you see here. So in the case of deliverable 1, I have a single file called main.txt, and I wrote into that document all the steps that make up deliverable 1. So in the case of Overleaf here, I'm choosing a coarse-grained ontology. What do I mean by that? Let's come back here for a moment. In my case, I'm choosing just one category. I'm just going to have one file, and there's going to be a whole lot of individual steps describing the deliverable inside that LaTeX document. Because for most of the deliverables, it's a relatively flat list of a large sequence of hopefully simple steps. So I have a particular activity in mind. I want to write a lab or a deliverable, which is a set of individual small steps. So in this case, I'm creating my own ontology inside of Overleaf, which is one document, and in that document, I got a whole bunch of simple steps. It's a coarse-grained ontology. Alternatively, I might be writing a report for school, or I might be writing an academic document. And in that academic document, I'm going to have a various number of sections. I'm going to have an introduction. I'm going to have a section on methods, and possibly a third section on results. And there we go. So I just compiled it. So now on the right, I have a PDF with these 3 sections. This is a sketch of a paper. As I'm writing this paper becomes increasingly long. And I start to think about these sections not as sections anymore, but maybe chapters of a book. This is going to get very, very large. So as I continue writing the introduction, for example, perhaps it's no longer a couple of paragraphs, it's a couple of pages. And the same thing for methods. So this one document, this one main.txt is becoming extremely long. I'm writing inside of this document, and this document contains 100, 200, 300 pages. My activity is changing. I've gone from writing a simple document into writing a book. And at that point, I might want to try and organize the book a little bit more and switch from a coarse-grained ontology to a fine-grained ontology. So imagine that my introduction here is very long. So I'm going to create a new file called intro, if the internet holds up for me here. I'm going to cut and paste into this second document now, intro.txt, all of my intro. So my intro is maybe 20 pages, which is better than 300. I go back to the main document and I tell LaTeX to input this file. Oh, it's complete. Okay, good enough. And hopefully, if I recompile this, I get exactly the same thing. Why would I want to do that? Why am I breaking this up into bite-sized chunks? Makes it easier to work on.
So when you're working on another section, you don't get distracted by what you previously wrote.
Exactly. So I'm happy with my introduction. It's 20 or 30 pages long. I want to move on to methods. Every time I make a change to methods, however, I don't want to have to try and scroll through the 20, 30 pages of intro down to the methods part of the PDF. So I comment out the intro section, and for the moment, it's not included in the PDF, right? So there have been a lot of innovations over the years in software development, like commenting and uncommenting parts of the code, which you're probably doing with your deliverables quite a bit these days, right? So I'm borrowing some of the ideas from the ontology of software development for writing a long technical document like a textbook, for example. As this process continues, I'm going to have a growing number of files here. So my ontology is becoming more fine-grained. I'm cutting things into smaller and smaller pieces. As I'm writing this larger and larger book, however, I realize I want to go back and revisit the section on KNN. Where in the book is the section on KNN? Now we're talking about navigating an information space that I've been creating, and the information space in this case is the book and its associated documents and sections and text and paragraphs and so on. The nice thing about having a coarse-grained ontology, like the deliverable where everything is in one document, if I want to know where KNN is in this single document, I search for it. Right? Pretty simple, right? A nice advantage to a coarse-grained ontology is you have one or a few things and it's easy to search through them. The advantage of a fine-grained ontology is we're breaking things up into lots of small pieces, which is nice. But it's not always obvious how to look for something inside something that's hierarchically organized. For most modern IDEs and LaTeX and Overleaf, yes, you can do a global search and it'll find that in there. The point I want to make here is we're making choices about how to organize this information space and how to break it up into chunks. And those decisions have pros and cons. And we want to weigh those pros and cons based on what someone is trying to do. So let's go back now to our example about a train station. We want to create a timetable, maybe a paper timetable for our train station. We're going to try and keep things simple and choose a coarse-grained ontology. Every trip made by a train, leaving or arriving at the station, is going to be assigned to one schedule or one item. That item describes the train that leaves at time X, leaves station X at time T1 and arrives at Y at T2. So our schedule is going to be a flat list of a whole bunch of these elements, and each element in the list has 4 numbers associated with it. And that's what we post next to the ticket booth in the train station. Nice and simple. What's the problem or what's the drawback about that? Simplicity is the pro. What's the con?
Well, kind of looking ahead,
it could be a cargo train.
Could be a cargo train, right?
Or and there isn't room for you.
It's listed on there, right? So is this train a passenger or a cargo train? I can ask the teller at the ticket booth, but that kind of defeats the purpose of looking at the schedule. So I take my coarse-grained ontology and I add a fifth column, which is notes, right? So for every element in the list, there's an asterisk and it says, don't buy a ticket for this train, it's a cargo train, right? Double asterisks. This train contains no smoking, it's all non-smoking cars. So if you're a smoker, make sure you have a smoke before you get on the train, right? And. So we have a growing set of miscellaneous notes in the right-hand column. I hate smoking, so I want to just look at those elements in the list that contain all non-smoking cars. How am I going to do that? Not an easy thing to search for, right? Pros and cons.
I really like, I don't know if anybody's taking Caltrain.
What's Caltrain?
Caltrain is how you get from like San Francisco to Silicon Valley.
Okay.
And early in the morning, a lot of people are coming in and they explicitly show you which trains are express trains, which the normal trains take 45 minutes longer than if
Okay.
you jump on the express train. So it's really important for people who are traveling and need to get somewhere on time to know this train is going to get you there the fastest.
Absolutely, right? So cargo versus passengers may be a tongue-in-cheek example, but express versus the milk run that stops at every local station, that's very important for most people performing this activity. Okay, so instead, we start to make increasingly fine-grained, we start to create an increasingly fine-grained ontology for our train station schedule, and we add a column for express/milk run. And first class, does it contain first class trains or not, cars or not? Which stations does it stop at along the way? We keep adding columns to our schedule, which provides relevant information for our travelers. What's the drawback? Why not just always do that?
It's just too busy.
It's too busy, right? Remember our discussion about visual design. We're adding more and more ink to the schedule, which is helpful, but there's this very fine trade-off, right? Hard to strike that balance well. Okay, so we talked about this. You can come up with your own pros and cons. In the case of coarse graining, advantages, it's simple. We have a new train or a new train that's been added to the schedule. It's easy to add it to the coarse grain list, right? Where does it leave and when, and where does it arrive and when? Done, right? Okay. However, we get vague category descriptions, complex objects. We have to add additional metadata and notes and so on. It becomes increasingly difficult to organize. So maybe we switch to fine grained. We have very sharp category divisions, but we have many categories. We're projecting a lot of information. I'm looking at the schedule. It's hard to figure out what is the shortest path from A to B. No right answer here, just again, to think about these and who is using this information. Okay. So we just talked a little bit about ontology, and for most of you, you might have the pleasure of getting to work with a brand new type of technology, which is extremely useful, but not immediately obvious to new users. You might get to sit down with your fellow developers and participate in the creation of a brand new ontology. This isn't a new operating system, so files and folders aren't relevant. It's not a Git version control type thing, so trees and branches aren't relevant. What is the right ontology for this new technology? Once you create an ontology and you deploy it out in the world, users are then going to not modify the ontology. You can't get rid of files and folders on a desktop. You can delete individual files and folders, but you cannot delete the concept itself. The ontology is fixed. What the user can change is their taxonomy, how they go about organizing objects to fit into the ontology that you create. Right? So we all have a desktop on our various platforms. We all have files and folders, and we all organize it differently. Some of us don't organize it at all. In my case, I have my root folder, and then I just have years. 2013, 2014, 2015. I mostly use my computer for academic purposes. So inside each folder, there's a research and teaching subfolder. What do you think is inside the teaching subfolder? This course, right? So you already get my taxonomy, right, which I am plugging into the ontology. You probably all have very different taxonomies. In the Overleaf example that I gave you here, you could think about this breaking this book that I'm writing into different files and so on as a taxonomy. The ontology of Overleaf and LaTeX is documents, sections, text, paragraphs, sentences, words, and so on. And I am creating different structures inside that ontology. I'm creating different taxonomies. Okay. Finally, we have epistemology. Yes?
When you do the organized desktop icons by size, type,
Yep.
information, is that actually an ontology because it's already predefined for you, or is that a taxonomy because you're defining it yourself?
So if you organize your files by size and you list them from largest to smallest, for example, you are making use of additional parts of the ontology, which is file size, right? Files have a size. The fact that they have a size at all is a part of the ontology. You sort your files on your computer from largest to smallest, and Crystal sorts hers from smallest to largest. You're both using the same ontology, but different taxonomies. You're organizing and grouping the information differently inside your two different information spaces. Okay. I just mentioned that, yes, question?
Doesn't ontology indicate boundaries are non-existent? Don't files inherently have some memory boundaries?
Exactly, that's right. Right, so a file has a boundary, right? It's a thing that has a physical extent.
Does that push file size into taxonomy instead of being classified as ontology?
The word file size itself. When they were creating, when GUIs were being invented, right, and they came up with files and folders, right, they realized that more or less material was going to be put into these files, like text or figures and images and equations and so on. So there's more and more stuff going in there. I could open a file and scroll through it to see how much stuff is in there. But for most purposes, I would rather just see the size of the file, right?
Okay, so when we developed RAM, when we developed some sort of memory system, file size became an ontology. But the actual size of the file is a taxonomy.
Yes, correct. So you take an individual file and you ask, what is the size of that? That's now more about taxonomy. I'm going to take all files above 1 megabyte and put them over here, and all files below 1 megabyte and put them over there. That's taxonomy.
I think there is a very good analogy. The ontology is
The ontology,
kind of, yeah, ontology is a class, and the taxonomy,
Yep.
yeah, is the instance.
Ah,
So
good
you-
example.
yeah.
Okay, so let's talk about that one, right? Object-oriented programming. For some of you, this is a new concept. And in object-oriented programming, there's an interesting ontology. That ontology is populated by class and instance. Both class and instance are part of ontology. Why? Why is it not what you said, which is class is ontology and instance is taxonomy?
Because again, it's the same circumstance. When the method was created and communicated, that determined an ontology, a way of thinking.
Exactly.
Advancement in that thought process is entity-dependent system, which is still an ontology.
Exactly. So the history of OOP is interesting in and of itself, so we're just going to very briefly talk about this. In the old days before OOP, you wrote your code and there were like functions and variables. There was some sort of modularity that was useful. But with the idea of OOP was this idea of abstraction, right? So when you write code without OOP, you tend to have a lot of methods or functions, sorry. You create a copy of a function and then modify it, right? And now those two functions are separate from one another, right? So you start to get this branching idea that we talked about in Git. Wouldn't it be nice if you could somehow organize things so that these two functions are still related somehow? We want to abstract away the differences between these two functions and exploit the commonality about them. So let's create an ontology, and in that ontology there are two important conceptual objects, class and instance, right? And the idea in that ontology is you can make multiple instances of a given class. That's ontology, right? The fact that those two ideas exist in the same way that files and folders are the base parts of the ontology for a desktop. Now you sit down and start to write some object-oriented code, right? And you decide in your object-oriented code you're going to have 5 main classes. And for each of those classes, you're going to generate multiple instances. That's taxonomy. How many classes are you going to have? And how many instances are you going to spawn of those different classes is not that different from deciding on your desktop how many folders and how do I organize my files inside those folders. You can't escape classes and instances when you're writing object-oriented code. Yep.
So when we discussing the OOP itself,
yes,
the class and the instance becomes an ontology.
Ontology, exactly.
But when we are thinking about our ideas,
when you start using it, right?
Yeah, we can kind of because an instance is when we are thinking about our ideas.
Yes.
An instance is realization. A realization of a class. So that is an analogy.
That's a good point.
To this one.
So the distinctions between these are maybe not as sharp as I'm trying to make them sound.
Yeah.
You can sit down and have a vague idea for some code you'd like to write.
Mm-hmm.
You're in the messy world of human needs and wants, and you distill those down into specific classes and instances. So there is something about ontology that is going on there. That's right. That's a good point. Yes?
I feel like he was trying to make more of like an abstract analogy of saying like the class would be the fact that there's files and folders,
yep,
and like the instance of the class would be like your specific computer with your specific files and folders.
I think that makes sense also, right? Yeah, exactly. These distinctions are maybe not that clear. You can create a coarse-grained set of classes. You have a few classes and a large number of instances of any one class. Or you could create a fine-grained ontology when you write object-oriented code where you create lots of different classes and abstract classes and so on. Yes, so it is also about ontology. It's a good point. Okay, the discussion that we just had is an epistemological discussion, right? How do we go about deciding on a particular ontology? What's the difference between taxonomy and ontology, right? Those are all epistemological discussions. They're how we go about creating new knowledge or new things. It's an easy way to think about sort of epistemology. The practice of inventing OOP itself was an important epistemological exercise, right? Okay, not going to talk much more about epistemology, but if you hear that, that's the basic idea of bringing something into being that didn't exist before. It's a relatively rare thing in human domain, but when you write code, you're bringing something into existence that didn't exist before. But even more fundamentally, creating a new SDK for a brand new piece of technology, or an SDK for a cybernetic device. You need to decide on an ontology. What are the right basic conceptual objects and views onto those objects that you want to advertise to the user or the observer or the stakeholder? It's a very creative and interesting process and very difficult to get right. Okay. Let's talk about information spaces now and talk about their characteristics. And we're going to do this like when we talked about non-functional requirements for code. We're going to have a list of some of these things. And information spaces are often very abstract things, so we want to try and nail these down and talk about various aspects of information spaces. Let's start, as we always should in HCI, not by thinking about classes and instances and code and programming languages and the Leap device, but rather, what are people doing with this system? How volatile is the activity? And usually volatility dictates the coarse grain, the level of coarse grain or fine-grainedness in our ontology. Let me give you an example of that. Let's go back to the example of writing a textbook. Typically, if I am writing a textbook, I'm going to decide early on the chapters. There's 12 chapters, and these are the ideas that go into those chapters. At least in my personal experience writing very long documents, once you've decided on that top-level structure, that structure doesn't change very much. The content inside the chapters themselves might be volatile. I might write and rewrite them several times. But I'm probably not constantly changing this document to be 3 chapters, then 20 chapters, then 15 chapters. So there is low volatility at the chapter level of writing a textbook. So I choose a fine-grained ontology at this stage. I create individual files for these individual chapters. I'm chopping things into bits. Right? I'm fine-graining things. But inside the chapter, there's a lot of volatility. I'm writing and rewriting things. So it probably doesn't make sense for me to make files that correspond to subsections and sub-subsections inside the chapter. Because if I'm continually rewriting the chapter, I'm continuously creating and deleting files, right? I'm probably making more work for myself. So even in the same activity, albeit in a complex activity, writing a textbook, there's low volatility at the high level and high volatility down below, and that's influencing how I break up this task using this technology. So we're already seeing how thinking about the activity influences how we go about building this information space. You are going to participate in creating an ontology when you create the interface for your ASL game. Educational games have some obvious building blocks that usually go into them. What are some of the basic pieces of an ontology for an educational game? Someone mentioned Duolingo a few weeks back, right? What are some of the things you see in Duolingo? Points, okay. That's true of games in general. Educational games or educational software.
Like lessons or challenges.
Exactly, right? We borrow from non-technological education, chapters, sessions, lectures, questions and answers, and so on. Maybe we start to build some of those into our system. We'll end with this one here. We kind of mentioned this already. The size matters, right? So one of the things that your user is going to do with your system as they move through your ontology, as they navigate through it, is they want to find things. So your user is learning ASL through your educational game. Can they skip ahead to a later lesson or go back to an earlier lesson? How volatile is that? Are there new lessons being added all the time, or are there a few basic lessons at the top? Learn letters, learn digits, right? That's probably not going to change. Maybe the lessons underneath are continuously being added and modified by the developers. That all influences how you think about the activity. How do people find various things inside your ontology? I think we will stop there for today. You have a quiz due tonight. You're working on deliverable 5, and I will see you all on Tuesday. Thank you.